right, so we're just going to take care of section 2.1 quickly. It's pretty simple and just some definitions and quick little things, and some of them you already know. So there's two ways that you can talk about a matrix. You can obviously be given a matrix like normal, but you can also do like we had with the identity matrix earlier. Remember when we had E1, E2, and so on? So those were columns of the identity matrix. If somebody starts calling something A1, A2, those are the columns of matrix A. You can also name entries in a matrix. You can do it in terms of the entries right here. And so that goes like this, the ith row in the jth column. And so if somebody is, has a matrix, let's say 2, 3, 1, 6, 4, -1, 2, -2, how about 5, 7, all right? And this was called matrix A. If you wanted to talk about, let's say, this spot right here, that would be in the spot A. And what row is it? Well, it's the third row, and it's the second column. So spot A32. So not A32, it's A third row, second column. And so if somebody's talking about it, you start to see little things like that. So it's a definition. All right, and then you have something called a zero matrix in this next little bit right here. So obviously a zero matrix has all zeros, and so that's not that big of a deal. All right, so a diagonal matrix. This doesn't come into play that much in this section, but a diagonal matrix, but it will later. But when you have a diagonal matrix, it's just a square matrix, so it has to be 2 by 2, 3 by 3, so on. And the non-diagonal entries are 0. So what that means is that, let's say you had a 3 by 3 matrix, you'd have a number here other than 0, a number here other than 0, a number here other than 0, but everywhere else would be all zeros. So that's it. Equal matrices, same size and same entries. Okay. In order to add up two matrices or subtract two matrices, you have to have the same size because each one has to have its corresponding spot. All right. Also, there's scalar multiples. So that just means you multiply everything in the matrix by that number. All right. So here's some easy little examples here. So this right here is denoting I should go to matrix A and go to the second row, third column. So that would be right here. So the answer to this is 3. All right. Oh, why did I write that? 2. Sorry. Oh, God. All right. And then letter B says do -2 times A. So basically multiply everything in A by -2 right here. So I get -4, 0, and 2. And I get -8, 10, and -4. All right, and that's because then, like, let's say in letter C, I want to do B minus 2A, so just subtracting. So if I'm doing B minus 2A, that's like B plus -2A. I'm going to say that because I already have those two things right here. So I'm just going to add those together. So I have 3, and then, of course, -5, and then 3, and then 1, -8, -7, -4 and 10 is 6, and -3 and -4 is -7. Okay. All right, so you would already know how to do that. I'm pretty sure you knew all this already. So theorem 1 here is just going through some things that you already know. If you add two matrices in any order, that's fine. If you add 0 to a matrix, you get the matrix back again. If you multiply a scalar by the addition of two matrices, you can multiply each by the scalar first and then add. So there's a bunch of little rules that you would normally know anyway. And what you learned in your warm-up last time right here about multiplication is that matrix multiplication is not commutative. So if you have matrix A times B, it is not equal to B times A. Every once in a while it might equal itself out, but the general rule is it does not. So for example, if A is a 4 by 3 matrix and B is a 3 by 2 matrix, you guys already know that you have to have the columns in the first matrix has to match the rows in the second matrix so that you can actually do it. And then your answer is going to be a 4 by 2. All right. And so if you tried to reverse that, this was A and this was B, if you tried to do B times A, you'd have a 3 by 2, and then you'd have a 4 by 3, and it wouldn't line up. Oopsie. It wouldn't line up. And so automatically you would know that's impossible. Okay. All right. So on the next page right here, it's just remembering how to multiply matrices. So it's a good review in case you always forget. So remember, I'm doing my row times the column. So let's figure out the sizing first. This one is a 2 by 3, and this one's a 3 by 2. So I know that my answer is going to be a 2 by 2. So that helps me because I know I'm going to have 4 spots to fill. Okay, so this pink stuff up here, the 236 times the 204, is going to go in the first spot because it's the first row, first column, so it goes in the first row and first column. So 2 times 2 is 4, 3 times 0 is 0, and 6 times 4 is 24. So I'm going to put an old 28 in there. So then I move it over and I do over here. So now I have my first row, second column. So it's going to go in the first row, second column, right there. All right, so we got 2 times negative 3, so I got negative 6, and then 3 times 1 plus 3, and 6 times negative 7, negative 42. All right, so I get negative 48 plus 3, so negative 45. And then you move it down. I'm going to do second row, first column. So if I line that up and multiply it, you get 2, multiply and add. And then same thing for second row, second column. It's going to go in the last spot. I would get negative 4. I think you've seen all that before. Alrighty, so these parts here are just some little practice doing these. So, you know, we got a 2 by 2, a 2 by 2, and a 2 by 1. So first of all, when you're doing this, see if it matches up. You know, C times D, 2 by 2, 2 by 2 is going to produce a 2 by 2. So if you multiply those together, you get 113 across the top, and negative 7 and negative 6. So, you know, if you need to see that, you could stop for a second and go ahead and calculate it out. You'll see. All right, and so now D times C, so it does line up. You know, the 2 by 2 is still okay. I can do this, 2 by 2. So it's often nice to rewrite that because it's kind of backwards. So D is, you know, 3, 5, negative 1, 4. And times 1, 2, negative 2, 1, so like I had to do in your warm-up. So if I do that, the 3, 5 times the first column, I would get 3 and negative 10, so that would be negative 7. So I can already tell that, you know, I'm not getting the same answer. So if I do that, negative 7, 11, negative 9, and 2, so you can see that those are not equal. All right, D times E. So D times E, I got a 2 by 2 and a 2 by 1, so I'm going to have a 2 by 1 for an answer. Okay, so 3, 5 times negative 5, 3, I get negative 15 plus 15, so I get 0. And then negative 1, 4 times my 5, 3, negative 5, 3, I get 5 and 12, right? I think I covered up, no, yeah, 5 and 12, so 17. All right, and I try to do E times D. Well, E is a 2 by 1, and D is a 2 by 2. So that is not possible. All right, so matrix multiplication, there's just some properties down here that you can look through, but they're all pretty, you know, similar. The big one is that this is not true, or, you know, like A times B is not equal to B times A. All right. All right, and also remember that if you multiply, you know, in regular math, like if you do, you know, 6 times x is 0, so x must be 0. All right, that's not necessarily true. If A times B is 0, it's not necessarily true that A or B is 0. So don't think that that's true, you know, because there's some multiplying and adding going on. So just because you get a 0 matrix doesn't mean that one of the two things was 0. All right. So for instance, in number 4, find a non-zero matrix such that AB is equal to 0. So we're going to set that up in a little bit of a tricky way here. Let's see. So I have like 1, 2, 2, 4 times find a non-zero matrix B such that AB is 0. So, you know, I can multiply this. This is a 2 by 2. I can, how about do it 2 by 1? All right, so when I do this, and it has to come out to 0, 0. All right, I don't have to find another 2 by 2. It just has to be a 2 by 1. So let me put, like, how about x and y? All right, so if I make a problem out of this, my 1, 2 times my xy will be x plus 2y has to equal 0. And my 2, 4 times my xy has to be 2x plus 4y equals 0. All right, or we could go ahead and just set it up like this. We could have 1, 2, and 2, 4. Augment it with 0, 0. All right, and just go to our calculator. All right, so I put my matrix A in there. You can see that the rows are multiples of each other, so we're going to get infinite solutions here. So when I go ahead and do my RF, oops, on that. All right, you see I have infinite solutions. So y, in my case, can be anything, and x has to be -2 times that. So y is free, and x has to be -2 times y. So why don't we just make up one? Y is anything, so how about I say 3, and then this would be -6. So let's try it out. So 1, 2, 2, 4. So if I try that out, let's see. I would say 1, 2 times -6, 3. I would get -6 plus 6. So yes, I would get 0. And then my 2, 4 times -6, 3, I would get -12 plus 12. So 0. All right, so that's a just quick little fact thing. All right, oops, was I done with that page? No, I was not. All right, oh, where was I writing? Oh, there. I'm sorry. I got confused for a second. All right. So back to here. So powers of matrix. It's just a little quick thing, just to be sure that you don't think like falsely that powers of a matrix just imply doing the power. So remember, like if you have this right here, you don't just do 1 to the third, 0 to the third, 3 to the third, 2 to the third. It has to be written out. So powers of a matrix are really kind of a pain. Pretty much what you do, you multiply the first two together, and then you multiply the next one by that. Later there'll be like a little trick for it, but for now, that's all you do. So 1, 0 times the 1, 3 in the first column would be 1. And then 1, 0 times a 0, 2 right here would come out to 0. All right, and then the 3, 2 times a 1, 3 comes out to 3 plus 6, so 9. All right, and then my 3, 2 times 0, 2 comes out to 4. And then, of course, you would do that next multiplication to produce your answer right there. Okay. All right, and then we have this thing called the transpose of a matrix. So again, this is something that's like setting up something later on. So this is just a definition right now, the transpose. If you take every row of the column and turn it into every row and turn it into a column of a new matrix, that's called its transpose. You see the 5, 6, 7, 8 was right here, 9, 0, 1 is over here. All right, so that's just called A of t, or A to the t. All right, so if you, these rules right here, if you take a transpose and transpose it back, then you get your original back. So duh. All right, letter B. Turns out if you add two matrices and do the transpose, then it's just a transpose plus a transpose. All right, letter C, for any scalar, you can multiply it by A first, then transpose it, or you can do the transposition first and then multiply it by R. All right, and then this guy right here, if you multiply A and B and transpose it, it's the same as transposing B and transposing A and multiplying. So notice the order switched on the other side. The B and the A switched around. All right, so we just have some few little things to do here, and then we are finished, correct? Yes, we are. All right, so, and you can put these in your calculator also, but we got some easy little matrices here. So first I'm going to do AB, and then we'll transpose it. So AB, I have 1, 2, 0 times 1, 0, 2. So that comes out to, let's see, 1, nothing, and nothing, so 1. And actually, this is a 3 by 2, and this is a, I'm sorry, 2 by 3. 2 by 3, and this is a 3 by 2. So my answer will be a 2 by 2, so this is a little bit large. All right, so we said that was 1 and 0, so 1. All right, then 1, 2, 0 over there times 2, 1, 4. So I get 2, 2, and nothing, so 4. Then I do my 3, 0, 1 times a 1, 0, negative 2. So I get 3 and negative 2, so that's 1. And 3, 0, 1 times my 2, 1, 4. So I get 6, nothing, and 4. So 6 and 4 is 10. So transpose that. I would get my row turns into my column, so 1, 4. And then my second row turns into my second column, so 1, 10. All right. Okay. The next one, AT, BT. So let's see if it works out. The transpose of A. So if I transpose A, it's 1, 2, 0, and 3, 0, 1. Transpose B, I have, okay, so 1, 0, negative 2, and 2, 1, 4. All right, so let's see if it works out. This is a 3 by 2, and now this is a 2 by 3, so it's going to work into a 3 by 3. So if you multiply that out, you will get 7, 3, and 10, 2, 0, negative 4, and then 2, 1, 4. So remember, then it says to square that, and so I would put that in my calculator. 7, 35, 31, 98. 6, 2, 4, and 24, 10, and 32. So remember, to square it, you have to multiply it by itself. All right, this last one here. All right, so BT and AT multiplied together. So I'm going to use this rule right there. So BT and AT multiplied together is the same thing as A times B transpose. So I already did A times B earlier. So remember that one was right here. So I'm just going to take it and transpose it. So it's going to be 1, 4 and 1, 10 as my columns. And since we already did half the work earlier, we're done. All right, I'll see you in class. Bye-bye.